Okay. So yeah, pH4 plus and BH4 minus both has 4 electrons in the valence shell. Both central atom has 4 electrons in the valence shell, which is forming a shaped tetrahedron. So pH2 minus and NH2 minus both both. Yeah, P minus and NHN. If you are taking the central atom has 6 electrons in the valence shell. So 2 bond pair and 2 lone pair. Total 4. So what is the shape?
Bent.
Yes, bent. So HCN. HCN. In HCN, which one is the central atom?
I took C.
Carbon.
C. So what is the shape?
Is it linear?
Yes, it's linear. Because valence electrons 4. Number of bond pairs? Number of bond pairs?
Number of bond pairs is 2.
Since it is a triple bond, carbon triple bond N and forming one single bond, 4 electrons it's used. The 2 sigma bond is formed by using 2 electrons and the rest 2 electron is used for the formation of 2 pi bonds. So what is the number of lone pairs?
0.
0. So total 2. So the shape and the geometry both are same. It is linear. Okay, if I'm going to discuss everything, we can only cover this today class. So I will just ask NH2 plus and KH2 plus, what is the shape?
Bent.
Yes, bent. With how many lone pairs?
I'm 1 lone pair.
Yeah, 1 lone pair. SOCl2. SOCl2. What is the shape? SOCl2. Anybody? Okay, how will you find it?
I'm 6 valence electrons, 3 bond pairs.
Yeah, 6 valence electron, 3 bond pairs. Then how many lone pairs?
1.
Yeah. So what is the shape?
Tetrahedron.
Yes. Total 4. Total electron pair is equal to 4. So the shape is a tetrahedral.
Geometry is tetrahedral.
Yeah. Geometry it's tetrahedral. And what is the shape?
Triangle pyramid.
Yeah, triangular pyramidal. Those who have doubt, just ask now. Okay. I will not discuss this again. SO2Cl2.
Shape is tetrahedral.
Geometry. Yeah, the shape is tetrahedral. Geometry is also tetrahedral. Which means sulfur has 6 electrons and 2 Cl2 means sulfur has 6 electrons. 4 bond pair it's forming and 2 double bonds with 2 oxygen and 2 single bonds with 2 chlorine. So formation of 2 single bonds, 2 electrons, it's 2 electrons it's taken and a formation of 2 double bonds. So 1 double bond, 2 electrons it's needed and other double bond, 2 electrons. So 2 plus 2 plus 2. So total 6 electron it's used for the formation of bonds itself. So no lone pair. So it's 4, 0, 4. So the shape and geometry are both are same, which is tetrahedral. And what about POCl2, Cl3?
Shape is tetrahedral and so is the geometry.
Yeah, the same. 5 electron it's there. 3 sigma bond with 3 chlorine atom which for that which is using 3 electrons and 1 double bond with 1 oxygen. So for the formation of 1 double bond, which double bond means 1 sigma and 1 pi. So for the formation of 1 double bond, it is using 2 electrons. So total 5 electrons is used for the formation of 4 bond pairs. So 4, 0, 4 tetrahedral shape. And IO2F2 minus or XeO2F2. Yeah, both is having the same shape and geometry. What is it?
The shape is seesaw, geometry is trigonal bipyramid.
Yeah. Letitia?
Yes, ma'am.
Yeah, you have doubt on this? Or
No, XeO6.
XeO16, I had that.
XeO6 4 minus.
Yeah.
Yes, ma'am.
Okay. So XeO2F2 or XeO2F2 or IO2F2 minus. So if you are taking Xe or if you are taking I, both has 8 electrons because in this there is a negative charge. So both has 8 electrons. And if you are counting the bond pairs, it is 4. And then you have to count the electrons. So 4 bonds in that means 2 bonds it's formed with fluorine atom, which is single bond, and 2 bonds which is formed with oxygen atom, it is 2 double bonds, which is simply Xe, F, F, double bond O, double bond O. This is not the correct structure. So let's check it. Which one? What will be the shape? So Xe double bond O, double bond O. So the total number of electrons which needs to form this 4 bond pair. So 1 electron for the formation of 1 sigma bond, and 1 electron for the formation of this sigma bond. So total 2. 2 electrons for the formation of XeO bond. So 4. 2 electrons for the formation of XeO bond. So 6. So 6 electrons is used for the formation of 4 bond pairs. So the rest it's 2 electron, which means 1 lone pair. So total electron pair it's 5. So sp3d2 hybridization and trigonal bipyramidal geometry. And the shape.
Seesaw.
Yeah, shape it's seesaw. And 5, 1 lone pair it's seesaw. We already discussed, so I'm not going to tell anything. So it's seesaw.
Yes, ma'am.
Okay, XeO2F2 and XeO4 or IO4 minus. What is the shape?
IO4 minus geometry is tetrahedral, shape is also tetrahedral.
Yes, means 8 electrons and 4 double bonds are forming. So each double bond, 2 electrons is needed. So for the formation of 4 bond pairs, 8 electrons is using. So 0 electrons left, 0 lone pair. So total 4. Since it is 0 lone pair, shape and geometry are same, which is tetrahedral. And SeO2.
Geometry tetrahedral, shape is pyramid.
Yeah, geometry tetrahedral and shape is pyramidal. Yeah, Sc, oxygen family. So 6 electrons, right? 6 electrons and 3 bond pairs. SeOCl2. Those who have doubt, just ask now, okay? So valence electrons, 6 electrons are there. Number of bond pairs, it is 3. For the formation of 3 bonds, it's taking 4 electrons, which means 2 single sigma bond with 2 chlorine atom. The 2 electrons is used from the central atom. And for the formation of 1 double bond with oxygen, it is using 2 electrons. So total 4 electrons is used for the formation of 3 bond pairs. So the rest 2 electrons. So the lone pair, it is equal to 1. So total electron pair, it is 4. So the geometry, tetrahedral, and the shape, it is trigonal pyramidal. Next, SF2Cl2.
Ma'am?
SF2Cl2. Yes?
Ma'am,
Yes,
can you
ma'am.
repeat the answer for IO4 minus?
I?
O4 minus.
IO4 minus. If it is IO4 minus, or if it is XeO4, means in the case of IFO minus, means we will also take this negative charge on the central atom to count the electrons. So what will be the valence electron? 8 electrons, right? Is it clear,
Yes, ma'am.
Letitia?
Yes,
Like
ma'am.
7 electrons are there since there is a negative charge, so plus 1. So 8 electrons. And what is the number of bond pairs? It is 4. Number of lone pairs. 4 means 4 double bonds are forming. 4 oxygen, 4 double bonds. So 8 electrons it's needed for the formation of 4 bonds with 4 oxygen. So 8 electrons will be used for the formation of 4 bond pairs. So the lone pair will be, what will be the number of lone pairs?
And 0.
Yes, 0. So total pair 4. So the geometry and shape will be tetrahedral.
Yes, ma'am.
Is it clear? What
Yes,
about
ma'am.
SF2?
That trigonal bipyramid geometry and shape will be seesaw.
So the same with SFO. We already discussed SFO. Same it will be the like 4 sigma bonds. So for the formation of 4 sigma bonds, 4 electrons will be used. So 4 bond pair and 1 lone pair means 2 electrons left, which will be 1 lone pair. So 4 bond pair and 1 lone pair, total 5 and 5 1 means 5 means tetragonal. Sorry, trigonal bipyramidal will be the geometry and 1 lone pair. So seesaw. PCl3F2 and PCl2F3. What is the geometry or what is the shape?
PCl3F2, both geometry and shape are trigonal bipyramidal.
Yes, both geometry and PCl2F3. Both will be
Exactly
same.
same.
SeOCl2. Yeah, we already discussed, right? XeFO.
Shape is square planar, geometry is octahedral.
Yeah. XeFO, 8 electrons. Valence electrons, 8. Number of bond pairs, 4. 4 sigma bond. So 4 electrons will be used. So the rest 4 electrons, which will be 2 lone pair. So total electron pair, 4 plus 2, 6. XeFO. I think we already discussed this. 8, 4 bond pair. 4 electrons will be left, which is 2 lone pair. So total 6. Geometry, it is octahedral. And the shape is square planar. What about XeF6?
Shape.
Shape, it's not discussed, right?
Yes, ma'am.
XeF6, yeah. When you're considering XeF6, valence electrons 8, total bond pair 6 sigma bonds. Number of lone pairs, it will be 1, and the total electron pair will be 7, and the geometry will be pentagonal bipyramidal. Pentagonal bipyramid. And the shape, it is distorted octahedral. We'll call this as distorted octahedral or by X-ray studies, we found that its structure is distorted octahedral. Shape, it's distorted octahedral. The shape will be like this. Like its angle, it's 90 degree, and its shapes will be like this. This is the shape, which means the 6, as we know, there is 7. If we are following the VSCPR, we can say like pentagonal pyramidal, as we already discussed about. We can say like pentagonal pyramidal, like 72. Yeah, pentagonal pyramidal, and 1 lone pair is here. But the actual shape, it's not pentagonal pyramidal. It is, You don't want to study like pentagonal pyramidal. It is distorted octahedral or capped octahedral, where the six bond pairs is arranged in the six vertices of an octahedron, and the lone pair can be present between two bond pairs, between two bonds of XCF2. And it can be here, it can be here, it can be here, and it can either means between any of two XC bonds. And it is assumed like it is floating in the space in the XCF6. And that is called distorted octahedral. So the if the total electron pair is equal to 7, and if there is one lone pair, shape will be distorted octahedral or capped octahedral. Shape will be distorted octahedral or capped octahedral. Distorted octahedral or capped octahedral, and this is found experimentally that its shape, it's arranged like this, like 90 degree, almost 90 degree. Like the vertices of an octahedron, all bonds are arranged on the vertices of an octahedron, and the lone pair will be there in between two bonds, like in space, and it can be it can occur in between any two bonds, and it is assumed like floating between the bonds in space. That type of arrangement is known as distorted octahedral. Okay, yeah, that is the only example you should study, that distorted octahedral XCF6. No other thing will not ask. So XCF6, XCO2.
The shape is bent and geometry is tetrahedral.
Yeah, XCO2, 8 electrons. 4 electrons is used for the formation of 2 XCO bonds, and 4 electrons left, 2 lone pair, 2 bond pair, total tetrahedral, shape is bent. XCO6, 4 minus.
I had doubt in that one.
XCO6.
It has 12 valence electrons.
Yeah. Then bond pair. Bond pair.
6.
6. And lone pair is
0. Total electron pair 6. Shape octahedral. Geometry will be also octahedral. So you should first you should say geometry. So what is your doubt?
no, sir. So 12 valence electrons is possible.
Yeah, 12 valence electron is possible.
Okay.
Yeah, that's also like the existence of XaO6 4 minus. Yeah, it's rare. Like, that is, yeah, I'm not sure like the XaO6 4 minus, it's existing or not. And when I was writing this example, I just wrote that. Yeah, let's check it. XaO6 4 minus. Yeah, it's existing in nature. 4 minus has approximately, yeah, it's existing in nature. Like its existence is the 6 8. It's possible. XaO6 4 minus. What about XaOF2? What is the? Yeah, it's possible. No, it's existence nature, so it's possible.
Okay.
XaOF2. Yeah, make it fast. XaOF2.
Geometry is trigonal bipyramid. Shape is T shape.
Yeah, okay. 2, yeah, 3, 5. Shape is T shape, right?
T-shape.
XaOF4.
Octahedral geometry and square pyramidal shape.
Yeah, 5 plus 1 square pyramidal. XaOF6.
Geometry and shape are pentagonal bipyramid.
Yes. XeO to F2.
Geometry and shape is octahedral.
Those who have doubt, just ask now. I will explain that molecule. If you don't, means if you're not asking, I will think like you don't have any doubt. Okay. XeO2 F2. What is the shape and geometry?
Both are octahedral. No, sorry, ma'am, I read the wrong one. I read XeO to F4.
Yeah, XeO2 F2. What is the shape and geometry? So 2. I think okay. XeO2 F2. 8.
Four.
Bond pairs 4. 6 electrons used. 1, 5. So right.
Yes, ma'am.
XeO2 F4.
Shape
Both
and
are
geometry octahedral.
Yeah, XeO3.
Tetrahedral geometry, pyramid shape.
Yeah, tetrahedral geometry, pyramidal shape. 6 electrons will be used for the bond pairs and 1 lone pair. So total 4. 3 plus 1, total 4. 4, 1, pyramidal, trigonal pyramidal. Essential for?
Tetrahedral shape and geometry.
Yes. Essential to?
I think it's trigonal planar shape. No, geometry.
Yeah, trigonal planar. Sorry, trigonal planar geometry, right?
Yes, ma'am. Trigonal planar geometry.
Geometry and bend shape.
Yes, ma'am.
Yeah, that is all about VSCPR. And what about that homework? The bond order.
Ma'am, what was essential to?
Essential to it is valence electrons 4, number of bond pairs 2, number of lone pairs 1, total electron pair 3, geometry, trigonal planar, shape, bend or V shape.
Yes, ma'am. Got it.
Okay. Trigonal planar, bend or V shape. Trigonal planar, geometry, bend or V shape. Okay, so what about this? What's your answer? ClO4 minus and PO4 2 minus? What is the bond order in ClO4 minus? What is the bond order in ClO4 minus? Tell me. How many resonance structures are possible?
4.
4. And so how will you find this bond order? What is the equation? So ClO4 minus. So 4 resonance structures. So Cl double bond O, double bond O, double bond O, and O minus.
7 by 4.
Yeah, you can draw 4 resonance structures. Bond order. What was the bond order equation to find bond order in resonance structures or resonance compounds? What is the equation?
The total number of bonds between atoms divided by the
Between
number
two
of
atoms, yeah, in all resonance structures divided by total number of resonance structures. Okay, so what is it?
7
7
by
by 4.
Yeah, 7 divided by
4.
4.
4. So what is the answer?
1.75.
Yes, 1.75. 1 3 by 4, so 1.75. So PO4 3 minus. PO4 3 minus, the same will be there. Like the number of what will be the number of resonance structures? First, you draw one structure like PO4 2 minus. If they are asking PO4 2 minus, you can just found like 3 bonds are similar and one is different. And you can just imagine like you can draw the resonance structures with different arrangements of this bond because 3 other bonds are similar. So it will be 4C1, which is equal to 4. So 4 resonance structures are possible. And I will say like without calculation, I know 4 resonance structures are possible. And in 4 structures, if I'm considering these 2 bonds, and in one structure only I will get this double bond. So it will be 5 by 4. Or you can draw this structure. As we know, only one double bond will be there in one structure. So total 4 structures are possible, and in only one structure, I will get a double bond between phosphorus and oxygen. And in all other structure, there will be sigma bond. And in this case, there is only one sigma bond, and all other are double bond. So in all 4 resonance structures, only one structure I will get a sigma bond between. If I'm considering these 2 atoms, I will get only in only one case I will get a sigma bond with ClO, and in other 3 structures there will be double bond with Cl and oxygen. So the total will be 2, 2, 2 plus 1. Here it's in only one structure I will get a double bond between phosphorus and oxygen. And in all other structure, there will be sigma bond. If I'm considering these 2, or if I'm considering these 2, anything. So it will be the resonance structure. Is it clear what I'm trying to say? Is it clear for you?
Yes, ma'am.
So PO4 3 minus, the resonance structures will be, yeah, you just draw that, okay? O minus, 4 structures are possible. O minus, double bond, O minus. So the bond order will be, if I'm considering these 2, 2 plus 1 plus 1 plus 1. So 5 by 4 is equal to 1.25. So what is the bond order in, what was the other homework? It was SO4 2 minus, right? Yeah, what is the bond order in SO4 2 minus? Sorry? Zero? SO4 2 minus, what is the bond order? Anybody? Or how many resonance structures are possible?
4.
No.
6.
Yes, 6. It is 4C2. You can consider like 4 bonds are there and 2 are identical. So it is like how many arrangements are there. 4 means in these 4 places you have to arrange different arrangements of these bonds. Considering it will be 4C2 and it will be 6. It is a combination and permutation and combination. I hope you know this in maths.
No, we haven't done it yet.
Okay, then leave it. Okay, then leave it. You don't want to study this 4C2 and just leave it. And if you have to, means you can draw this. If you are drawing also, you will find this 6. Yeah, I think I already drawn this structure SO4 2 minus. Just try to draw the 6 resonance structures. It will be possible. 6 resonance structures will be there. So what is the bond order? What is the bond order? What is the bond order? Anybody?
Ma'am, is it 5 by 3?
Is it
10 by 6, 5 by 3.
10 by 6 or 9 by 6?
Ma'am, yeah, it's 9 by 6.
Like, Like in 3 structures, there will be double bond. And in 3 structure, it will be single sigma bond. If you are considering one sulfur and oxygen in every structure, it will be like in 3 structure, it will be double bond between them. And in 3 structure, it will be sigma bond between them. O minus, double bond, O, double bond. O. So if you are counting 2 plus 2 plus 2, 6. So okay, 2 plus 2, 4, plus 2, 6, plus 1, 7, plus 1, 8, plus 1, 9. So 9 by 6. It is equal to 1.5. Okay. Okay, that's all about bond order. And also you have to, as we know, the bond order is directly proportional to bond energy. And also bond order is inversely proportional to bond length. Also note this. If the bond order is higher, like let's consider carbon, there is a molecule which has carbon-carbon sigma bond, and there is a molecule which has carbon double bond carbon and carbon triple bond carbon. The energy needed to break this bond will be higher for this. Because here it is 3 bonds, and if the bond order is higher, the energy needed to break that bond will be also higher, which means bond order is directly proportional to bond energy. And also, if you are considering the bond length, it's less for triple bond, which means bond order is inversely proportional to the bond length. So you should study this relation. Bond order is directly proportional to bond energy, and bond order is inversely proportional to bond length. And there is one question. Okay. Arrange the following in the increasing order of their bond length. In the increasing order of their bond length. In the increasing order of the bond length, CO, CO2, and CO3 2 minus. Yeah, just do it. CO, CO2, and CO3 2 minus. Arrange the following in the increasing order of their bond length. So just draw all those structures, then it will be fine. Like you will get the answer if you know the bonds. What is the bond between these 2 atoms in this molecule? If you know that, it will be clear. Like it will be easy. Anybody? Please try. Those who know the answer, just please tell me what is the answer. First, you arrange in the order of bond order. Then it will be easy to arrange in the order of bond length, because it will be opposite. Because as we know, bond order is inversely proportional to bond length. So what is this bond order in CO?
Will be 3.
Yes, it is 3. And the third, it is a coordinate bond, and we already discussed it. So the bond order of CO, it's 3. And CO2?
2.
2. Yeah, means CO2 means we are measuring the carbon oxygen. Okay, arrange the following in the increasing order of the carbon oxygen bond length. So the carbon oxygen bond order, it is 2. And CO3 2 minus. What was the bond order? We just calculated now. What was it? No, we haven't, right? So just calculate CO3 2 minus bond order. How many resonance structures will be possible?
Ma'am, is it 1.33?
Yes. How many resonance structures will be possible? 3, right?
3.
3.
So in that 3, if you are considering one carbon and oxygen, in one structure it will be double bond, and the other 2 structure it will be sigma bond or single bond. You just draw it and it will be clear. So 4/3, which is 1.33. So the average bond order it is 1.33. So if you are arranging these molecules, these compounds in the order of bond order, it will be CO is greater than CO2 is greater than CO3 2 minus. Then what will be the bond length order, increasing order of the bond length?
The
Which one is having? Yes,
CO3 2 minus is largest bond length, and then
CO3 2 minus,
CO2, and then CO.
CO2, then CO. This is actually decreasing order. Yeah, it's fine. Yeah, CO3 2 minus, it's having the highest bond length, and then CO2, then CO. And also, if you're calculating the CO2, if you're telling about CO2 also, the bond length, when you're considering CO2, the bond length between carbon and oxygen, it is found to be 1.5 picometer. Okay, is there in your it's there in NCRT text, the resonance structures of CO2, which means when you're considering CO2 molecule, the bond length, we found the bond length of between carbon and oxygen experimentally, and it's found to be 115 picometer. But the normal carbon double bond oxygen bond length is 121 picometer, and the carbon triple bond or bond length is 110 picometer. So we found that the bond length between carbon and oxygen is in between the carbon oxygen double bond and carbon oxygen triple bond, which means carbon dioxide is also involving in resonance, or it is not the actual structure, means it is also involving in resonance. And there is 3 resonance structures which possible for carbon dioxide. Why we have drawn this resonance structure, or how we found that the CO2 is involving in resonance, it's just because we measured the bond length of carbon oxygen, the bond length between carbon and oxygen, and we found that it is 115 picometer, which is in between, which is an intermediate value between carbon oxygen double bond and carbon oxygen triple bond length value. So the carbon dioxide is also involving in resonance, which is involving 3 resonating structure, which means carbon, double bond O, double bond O. The rest structure will be like, since it is between triple bond and double bond, there will be some triple bond character also, which means carbon triple bond oxygen and sigma bond oxygen, where it will be O minus and O plus. O minus and O plus, and the same thing. These are the resonance structures of carbon dioxide. And when you are calculating the bond order, what will be the bond order? Yeah, let's consider this oxygen and this carbon. What will be the bond order? Yeah, bond order it's remain 2, but the bond length is not as same of carbon oxygen double bond. It is also having some partial character, but when you are calculating the overall bond order, it is 2 only, because 2 plus 1 plus 3 divided by 3, which is equal to 6/3, it's equal to 2. So the carbon oxygen bond order it's 2, but it's also having some resonating properties. Resonance is also involving in carbon dioxide. You should also know this. And in the resonance structure, yeah, you should remember that the resonating structures which we are drawing, it is not the actual structure, or they are not existing as these resonating structure. Don't get confused, like these resonating structures are also existing in nature. The actual molecule which is existing in nature is representing by resonance hybrid. That is the actual structure. Okay, not like double bond, sigma bond means this is not, if you're considering carbon CO3 2 minus, it is actually like this. Both is having some double bond character. It is not like this carbon and oxygen will have some, for some time this carbon and oxygen will have a double bond, and after some time it will have double bond in between these two oxygen. And don't get confused, and there is no equilibrium between these resonance structures. Don't get confused like that. The actual structure of a molecule, it is resonance hybrid only, and resonance structures are like that is an imaginary one, and that is not existing in nature. Okay, that's all about bond order. And as we already discussed, resonance stabilizes the molecule. And if you are considering the energy of a resonance hybrid, energy of a resonance hybrid will be always less than the energy of canonical structures or the resonating structure. If you are considering any of the resonating structures and the resonance hybrid, the energy of the resonance hybrid will be always lesser than these resonating structures. So that's all about resonance and VSEPR. Now we are going to discuss about the bond length. So what is the bond length? I think this bond length, is it covered in periodic properties already?
I think we did we didn't do it in detail. We just did one example.
Okay. Actually, the bond length is defined as the equilibrium distance between two nuclei of two bonded atoms in a molecule. Like if two bonded atoms, as we know, the bond is forming between two atoms, and two atoms, if it is forming a bond between these two atoms, the distance, it is the equilibrium distance between these nuclei of two bonded atoms in a molecule. Okay, the equilibrium distance between two bonded atoms in a molecule. And when you are considering there is as we already discussed about overlapping, there is actually in covalent compounds, here we are concentrating on covalent compounds. So the simple definition of bond length in a molecule. Like if two atoms are involved in bonding, and the bond length is measured as the distance between these two centers, that we are measuring the bond length. And in covalent compounds, like if two atoms are forming bond, actually, as we know, let's consider, Cl2 molecule. So Cl atom is there, and another Cl atom is there, and it is forming a bond, so the nucleus, and this is the valence shell. Okay, as we know, the overlapping will be occurring in molecules when they are forming a bond. So after forming bond, they seems to be like this. It is not the actual thing. There is an overlapping, it's occurring. And the bond length is defined as the distance between, the equilibrium distance between the nuclei of two bonded atoms in a molecule. And also we know the overlapping will occur when they are forming a bond. So it will not be equal to the actual radius, the actual sum of radius of two atoms. If you are just considering the normal independent chlorine atom radius, if you know that, if you are just adding that, it will not be equal to the bond length in chlorine atom. because overlapping is occurring in between the molecule, in between the atoms when they are forming a molecule. So in that case, there is an introduction of term which is covalent radii or covalent radius. So covalent radius, we introduce it in terms in order to find the covalent bond length. So in the case of covalent compounds, we will already there is a standard covalent radii. We already found that, and that is in agreement with the covalent radius, covalent bond length, which means when you are finding a covalent bond length in a molecule, it will be equal to the sum of covalent radii. Okay, it will be equal to the sum of covalent radii. It will be equal to the sum of covalent radii. So, yeah, before I'm starting that, the covalent, just know this, what is bond length, and the bond length, there will be some difference. Like if you are measuring the normal independent atoms radius, if in the case of chlorine, in the case of Cl2 molecule, if you are measuring the normal chlorine atom radius, it is not possible, because chlorine will not exist as a normal chlorine atom in nature. It will always try to form compounds. Yeah, let's think like that. If you are finding the normal chlorine atom radius, it will not be same. Means if you are just taking the sum of these two chlorine atoms, it will not be same as the bond length. It will be a different value. Bond length is actually less than that, because the overlapping is occurring between two atoms when they are forming a bond. So, and also, yeah. Okay, we will discuss this later. So we will discuss the covalent radius first. So if you are considering, so in order to find the bond length in covalent molecules, we define the term which is covalent radius. So when you're considering the covalent, this is an atom core. Okay, this is actually an atom core. Or what do you mean by an atom core? Atom core means the portion which exclude the valence electrons, or when you're considering the covalent bond formation, the valence shell which is involving overlapping. So when you're measuring the bond length, we will exclude this valence electrons part. The atom core means the portions left after. Okay. Atoms core means the portion excludes valence electrons. So what is the correct definition? Yeah, portions excludes this valence electron. And covalent, when you're considering a covalent molecule, let's consider AB, and their bond length will be equal to Ra plus Rb. Since this is Ra and this is Rb, and Ra and Rb is known as covalent radii. Actually, the covalent radius is measured as approximately as the radius of atom's core, which means the core or the atoms which excludes these valence electrons. Atoms which excludes these valence electrons. Since the overlapping is occurring, it will be different. So in order to find the covalent radius, so atoms without valence electron. So covalent radius is measured as approximately the radius of atom's core, which means we are only measuring the radius without valence electron. Since the overlapping of valence orbital is occurring, so if the covalent radius is defined as the approximate radius of atom's core. Atom's core means atoms without valence electron. So covalent radius is measured approximately as the radius of atom's core, which is in contact with the core of adjacent atom in a bonded situation. Or in this case, we will consider it like the means we will exclude this valence, the orbital part, and we will only consider the core part of atoms, and that radius of atom core, we defined it as covalent radius. So covalent radius is approximately the radius of atom's core, which is in contact with the core of adjacent atom in a bonded situation. So since the overlapping is occurring, we will exclude these valence electrons because they are overlapping. So when you are measuring a covalent compound's bond length, it is the sum of covalent radius, and the covalent radius is measured as the radius of atom core, which is in contact with another adjacent atom's core when it is in a bonded situation. Okay, when it is in a bonded situation, okay, let's consider this chlorine atom. Actually, this chlorine atom is like this. Two chlorine atom, it's forming a bond by the overlapping of valence electrons. Okay, by the overlapping of valence orbitals. Since this orbital overlapping is occurring, we define this covalent radii in order to find the bond length in covalent compounds. And the covalent radii is defined as the radius of an atom core which is in contact with an adjacent atom core in a bonded situation. So when you are finding Cl2, which has a bond length of 198 picometer, then the covalent radii of Cl2 will be 99 picometer. It is actually the radius of atom core which is in contact with an adjacent atom core in a bonded situation. Why we are considering this covalent radii? Because atoms are involving in overlapping while forming bonds. Actually, this is the actual chlorine atom which include valence electrons. But when they are forming a covalent compound, orbital overlapping is occurring. Just because of that, we are considering only covalent radius, which is the radius of an atom core which is in contact with an adjacent atom core when they are forming a covalent compound. You should mention these things, like if you're mentioning like it is a radius of an atom core, that is not enough, because it is the radius of an atom core which is in contact with another adjacent atom when they are forming bond. Because in bonded situations only we are measuring this covalent radii, because its overlapping is occurring, so we are measuring the covalent radii in order to find the bond length of covalent compounds. So that is covalent radius. So the covalent radii definition, I hope it's clear. This is the radius of atom core which is in contact with the core of adjacent atom in a bonded situation. And what is van der Waals radius? Van der Waals radius, it's just the overall size of the atom. It represents the overall size of the atom, which means it represents the normal radius of an atom. So van der Waals radius represents the overall size of an atom, which means it is actually a normal radius of an atom, or it is the radius which includes valence shell in a non-bonded situation. So it represents actually van der Waals radius means the normal radius of an atom. So van der Waals radius represents the overall size of an atom which includes valence shell in a non-bonded situation. So covalent radii we will measure in a bonded situation, and van der Waals radius, it's actually the radius of an atom in a non-bonded situation which includes its valence.
When you're ending the class, just call me.
Okay.
At top.
Okay, 150.
150. I will never answer.
So what is covalent radius? Covalent radius, it's simply the radius of a non-bonded atom. Or we will measure the covalent radius in the case of non-bonded situation. It is representing the overall size of an atom. And sorry, okay, I think, yeah, I told the wrong thing. It is van der Waals radius. Yeah. Let's leave it. Is it clear?
Yes, ma'am.
I hope it's clear. So van der Waals radius is it's representing the overall size of an atom. It is actually the radius of a normal atom in a non-bonded situation. And covalent radius, we will talk about covalent radius in the case of bonded situation, or in the case of molecules are forming covalent bond by overlapping. That's why we are considering the covalent radius, and the bond length of covalent molecules will be equal to the sum of covalent radius. And the van der Waals radius, it is simply, if it is a chlorine atom is there with include valence electrons, it is simply the radius of an atom in a non-bonded situation. And also, if you want to find the van der Waals radius, you can also take like half of the distance between two similar atoms in separate molecule in a solid. Okay, I will write it here. Half of the distance between two similar atoms. As we know, the normal, like the independent atom existence, it's rare. Like we can't find a chlorine atom independent existent chlorine atom. So we will measure the van der Waals radius by taking half of the distance between two similar atoms in separate half of the distance between two similar atoms in separate molecules in solid. It's like this is a chlorine atom. So this is a chlorine and this is a chlorine. And we found the covalent radius, the radius of an atom core. And if you want to find the van der Waals radius, we will measure the distance between two similar atoms in a the distance between two similar atoms in separate molecules. Like there is no overlapping is occurring. Like as we know, the van der Waals force is the force which occur between two molecules which hold them together, like Cl2 atom. If you are talking about Cl2, means in the case of solid, these molecules are bonded together because of this van der Waals force. So the distance, the van der Waals radius, if you want to find the van der Waals radius, you just take, we will find the distance between the two centers of similar atoms in separate molecules in a solid. We will find this distance, which includes this valence shell also. So we will find this distance and we will take the half. So here, this 180 picometer is the van der Waals radius of chlorine atom, and the covalent radius, it is 99 picometer. So see the difference. So this is atom core radius and this is the normal atom radius, or which represents the overall size of an atom. So how we will find the van der Waals radius? We will take half the distance between two similar atoms and separate molecules in a solid. So two atoms, we will take the distance between the similar atoms in two different molecules, in two separate molecules, and take the half. So you will find the van der Waals radius, the normal radius of an atom. So how you find the van der Waals radius? This is the half of the distance between two similar atoms in separate molecule in a solid. And as we know, the bond length will be expressed in picometer or angstrom, and it can be found by using these techniques: X-ray diffraction techniques, spectroscopic techniques, and also electron diffraction techniques. So we will find this covalent radii and van der Waals radii, either the bond length, using bond length, covalent radii, or van der Waals radii, both all these things we are finding using these three types of techniques, which is spectroscopic technique, electron diffraction techniques, and X-ray diffraction techniques. So that's about bond length, and these are the covalent radii of some of the molecules, and these are single, means when they are forming single bond. These are the covalent radii of hydrogen, carbon, nitrogen, oxygen, fluorine, and chlorine. And then by knowing the covalent compounds, you can easily say the bond length. The bond length will be H2 will be 72 picometer, which is a sum of covalent radii of two hydrogens. These are the covalent radii of carbon, nitrogen, oxygen, fluorine, and chlorine. If they are forming single bond, okay, if they are forming single bond. So if you are taking carbon, C2 is not there, N2, yeah, N2 sigma bond is not there, so we can't find. So
Ma'am?
F2, yes.
Ma'am, if the bond length is the sum of covalent radii, I mean H2 should be 74, right?
Yeah, it's 74. Yeah, it's 74 only.
And should we keep in mind these covalent
No,
radii?
no. You,
Okay.
it's not needed. Like, yeah, I don't think they will ask this covalent radii and bond length and all those things. Normally, they will give this value if they're asking. I just wrote this to get to introduce these things. No need. You don't need to study these things. They will not ask. So 128 picometer. And if you want to measure the Cl2 bond length, it is 199 picometer. And the carbon in double bond state. Carbon double bond state, its covalent radii, it is 67 picometer. And carbon triple bond state, its covalent radii is 60 picometer. And oxygen double bond state, its covalent radii is 57 picometer. Yeah, it's not actually, it's not needed. Like, you don't want to study these things. It's not as much important, and it's not important. Just it is there in your text, so I just introduce these values. No need to study. Okay, just note it if you want. Just to get an idea. You don't need to study these things. So this is about covalent radii and bond length, and so we covered bond order, bond length, and bond energy. We are not going to tell anything, and bond enthalpy will be covered in detail in thermodynamics chapter. So bond energy, bond energy is the energy needed to break 1 mole of a bond in gaseous state, I guess. I didn't remember the proper definition. Yeah, it is the energy needed to break that bond. It's simply the energy needed to break that bond, and bond order is directly proportional to bond energy. And bond energy and bond enthalpy, it will be, yeah, it will clear in detail in thermodynamics chapter, and we'll study in detail, so I'm not going to discuss that. Now, the other one is bond angle. Bond angle, it's simply the angle between two orbitals which containing bond pairs in a the angle between two orbitals containing electron pairs around the central atom in a molecule or complex ion is known as bond angle. So that is the next thing we need to cover, the bond angle. So what is a bond angle? Bond angle, it is defined as the angle between the orbitals containing bonding electron pairs around the central atom in a molecule or complex ion. Or it is simply, if you are considering OH2, it is simply the angle between two bonds that we are defining, like it is defined as angle between the orbitals containing bonding electron pairs, which means the orbital containing bonding electron pairs is forming bond. So it is simply the angle between two bonds. And the definition, you can say it like it is defined as the angle between the orbitals containing bonding electron pairs around the central atom in a molecule or complex ion. NH3. It is simply the angle between two bonds, or the angle between two bonds of angle between two bonds which central atom is forming with other surrounding atoms. So it is simply the angle between two atoms, the angle between bonds of angle between two bonds which forms with central atom. The definition you can write it like angle between the orbitals containing bonding electrons with around the central atom in a molecule or complex atom. That doesn't matter. Like you just need the concept. It is simply the angle between two bonds. But if in exams, in normal exams, if they are asking the definition of bond angle, you just you need to write this. So that is only the bond angle thing, and the bond angle, it's not about the definition. You just need to understand how these bond angle will change, or how these how these lone pair existence or the surrounding atoms will influence these bond angles. How it is influenced by the existence of lone pairs or by the surrounding atoms, or by the OH2 means not OH2, H2O bond angle is 104 degree or 104.5, I guess, and NH3 is 107. Why it's like that? You need to know that. So arrange the following in the increasing or decreasing order of the bond angle. So I hope you can do this. Yeah, just do the first one. Find the bond angle. No need to find the bond angle. Find these structures, find these shapes, then you will get an idea about these things. So what is the shape of NO2, NO2 plus and NO2 minus? Shape of NO2, NO2 minus and NO2 plus. Then you will get.
Ma'am, these shapes, do we find them using shapes? Or
We can't find it using VSCPR concept, right?
wait, ma'am. So do we use Lewis or VSCPR?
No, it's VSCPR.
All right.
Shapes. We have to tetrahedron. Is it? No. Yes. Yes. So when you are considering NO2 plus, what is the shape and geometry? No need to talk about geometry. What is the shape? You need to know the geometry, but here we are only concentrating on shapes or the bond angle. Okay, just discuss proper. So valence electrons, 4. Bond pair,
2.
lone pair, 0. Total pair, 2. So the geometry and shape both are linear. Linear means 180 degree bond angle. The next is NO2 minus. Valence electrons, 6. Bond pairs, 2. Lone pairs, yes, 1. Like 2 double bonds, 4 electrons used, 2 electrons remaining, which is forming one pair. And the total pair, it is 3. So the geometry, it's trigonal planar. So the shape is bend or V shape. So what will be the bond angle? Means just say it will be less than 20 or greater than 20 or equal to 20. It's not equal to 20, 120. Less than 120, equal to 120 or greater than 120. What it will be?
Less than 120 degrees.
Ma'am, less than.
It is less than 120 due to the presence of lone pair. Due to the presence of lone pair, when I'm drawing this structure, I will draw like this only, okay? means you also, because we are considering these 6 electrons to understand the geometry and shape. When you're drawing this structure, we will follow this method only. So someone joined. Oh, I lost my internet connection. So NO2, as we already discussed in the drawbacks of Lewis octet theory part, NO2, it is an odd electron species, which means NO2, like 5 electrons it's there, and bond pair it's 2, and lone pair, it is not a lone pair, it is a 1 electron existence. Odd electron existence is there in NO2. It is not a lone pair. NO2 is also having a type of bend shape. Okay, double bond O, double bond O, and there is a 1 electron. And if you're finding this angle, it is actually more than 120 degree. Because due to the presence of single electron, as we know, when you're considering the existence of 2 electrons and the existence of 1 electron, the repulsion which is causing due to the 1 electron, it will be less, and the bond angle of NO2, it's actually greater than 120. Okay, or you can, when if you don't need to. You don't need to study this. It's like greater than 120, or when you're comparing, you will get an idea. Like it is in the case of NO2 minus and NO2 plus. NO2 has only 1 electron, whereas NO2 has a pair of lone pair. No, sorry, a lone pair, which means 2 electrons is there. So the repulsion will be more here. So the bond angle will be less here. The repulsion will be more here due to the lone pair. So the less, so it will form a bond angle. Means its bond angle will be greater than as compared to NO2 minus, or actually its bond angle is something 130. Yeah, 134 something. 134. It's approximately 134. It is actually due to the presence of lone pair. Or when you're comparing also, means without knowing this bond order value also, you can say one is linear and the other is NO2 minus and NO2. Where NO2 minus has a presence of 1 lone pair, where NO2 there is only 1 electron. So the repulsion in NO2 minus will be higher due to this lone pair, so the bond angle will decrease. But here there is only 1 small electron, so its repulsion will be minimum. So the bond angle will be greater here. So the comparison of bond angle, what it will be? NO2 minus, NO2 plus is having high S bond angle, which is greater than NO2 is greater than NO2 minus. Or in normal cases, if the same molecules plus neutral and negative is asking for the comparison of bond angle, actually it will be like this. Means normal trend is like this. Means this is for your competitive exam, you can study like this. Like when you are comparing O3 minus O3 and O3 plus, the bond order will be more for this plus charge one, and the not bond order, bond angle will be more for this O3 plus, then O3, then O3 minus. It should be the same molecule, okay? If the same molecule plus negative and neutral is asking, the bond angle order will be like this. Normally, this is not for your NCRT. Like if you are preparing for JEE and some questions like this is came, you can just remember this way: minus, plus, and positive, just like the number system. The negative, it's having least 0, then positive. Positive is having the highest value of bond angle. Then 0, then negative. Okay, then consider the O3 minus, O3 and O3 plus bond angle. So tell me the shape and geometry. What about O3 minus? What is the shape and geometry? Just find it. Is it clear for NO2 plus, NO2 and NO2 minus how we are comparing the bond angle?
Yes, ma'am.
Okay, then find O3 minus, O3 and O3 plus, or just compare these bond angles.
O3 minus has more than O3 and O3 plus has the least.
O3 minus has more. No.
No, sorry, least.
Yeah, it will be like this. I already told you this shortcut. No, I'm telling like just find the shape and geometry. What is the shape and geometry of O3 minus? What is the central atom? Central atom is oxygen, right? So what will be the valence electrons?
7.
Bond pair? Bond pair. Is it? You should consider the central atom and the surrounding atom. The bond pair, it's equal to the number of surrounding atoms. If you are considering 3, where is the central atom? So it will be oxygen is the central atom and 2 oxygen is the surrounding atom. Don't get confused in the case of I3 minus, I3 plus, O3 minus, O3 plus. It is not 3, it is equal to 2. It is actually oxygen is forming bond with 2 other oxygen. This is the structure of O3. So what is the number of bond pair? 2. Then number of lone pair? Yeah. Okay, I think it's just leave it like. Yeah, it is also an exception. Like O3 minus structure, we can only explain using MOT. And the lone pair will be 1 lone pair and 1 electron will be there. And in the case of O3, it is 6, 2, and 1 lone pair will be there. And in the case of O3 plus, 5, 2, and 1 electron will be there. Here 1 lone pair and 1 electron will be there. Okay, I think it's better to leave it, or you just study this order. O3 minus, it's less than O3, it's less than O3 plus. You don't need to study this much, like 1 lone pair and 1 electron, and this structure, it's actually its explanation, we can run it by MOT. And after explaining MOT, we will discuss this once more, like O3 minus, O3 and O3 plus. So there is existence of 1 electrons is there, and if you are comparing this repulsion will be more here. So means less bond angle, and then so repulsion will be more here. Then this, because 1 lone pair, then this is 1 electron, then this. So the bond angle will be, repulsion is minimum here. So the bond angle will be higher for O3 plus, then O3, then O3 minus. So the order is like this: O3 plus, it's having a high bond angle than O3, than O3 minus. Yeah, the geometry and shape prediction, it's difficult. You can directly predict this O3 because we are not dealing with electron pairs in VSCP, means odd electrons in VSCPR. That is one demerits of VSCPR actually. Like we are only dealing with pairs. So we are not discussing these things in VSCPR. You can say this is better. But the comparison we can tell, like O3 plus it's greater than O3, it's greater than O3 minus. Since the repulsion is minimum in O3 plus. The next question. Okay, second question was this. Compare the angle between NH3, CH3 and H2O. NH3, CH3 and H2O. CH4, NH3 and H2O. Arrange the following in the increasing order of the bond length. Arrange the following in the increasing order of the bond length. What is the answer? Arrange the following in the increasing order of the bond length. What is the answer? Anybody? Or do I need to call someone?
Ma'am, just a minute.
You know these things? I think it's very good.
I'm finding the shape. just a
Both.
minute.
Not NH2. Okay. Oh, that's what's okay. NH3. Minus. Sorry. Then I guess you can just say simply LCH4, NH3, NH2. Both three are sp3 hybridized.
Ma'am, so in increasing order, would it be H2O and H3
Both
and
is
CH4?
H2 is
Voice is
okay. Is it okay now? Oh, I just. Hello?
Yeah.
Hello? Okay.
Ma'am,
So,
your voice is fine,
yeah,
but the
both is
video is
having
freezing.
sp3, both three. Video, my video. It's
Ma'am,
like
it's freezing.
the slides of my video.
Ma'am, your video, it's
Video,
freezing.
it's okay. Okay, that's okay, right? You can't see the slides or
Ma'am, that's
slides,
fine.
it's also,
Slides are fine. Slides are fine.
yeah, then it's fine. Like, some internet issue is there, so yeah. So within 30 minutes we'll finish. So it's fine. So yeah, both is having sp3 hybridization, tetrahedral geometry. When you're considering CH4, tetrahedral regular geometry, 109 degree, 28 minutes. And when you're considering NH3, existence of one lone pair in the tetrahedral geometry. When you're considering H2O, existence of two lone pair in the tetrahedral geometry. So the repulsion will be maximum in H2O. So the bond angle will be minimum. Means the repulsion due to lone pair is maximum. Due to the existence of two lone pair, the bond angle between oxygen and hydrogen will be minimum 104.5. And in the case of NH3, there is only one lone pair. So the bond angle, bond angle is 107 degrees. So the comparison in CH4 is having NH3 and H2. No need to, you don't need to study these bond values. You just need to understand the concept to compare these bonds. Okay, to compare the bond angle. No need to study these values, and the H2 and NH3 it's standard value, so everyone will know. So what about these Ni3, NCl3, NBr3, and NF3? Before comparing that, I need to tell you one more thing, which is when we are discussing about the VSEPR, I told you lone pair repulsion. Lone pair repulsion is higher than lone pair bond pair repulsion is higher than bond pair repulsion. That we already discussed. Okay, it's fine. The next one was existence of multiple bonds. Well, and we already discussed how we will arrange these lone pairs, how we will arrange the lone pair in a molecule. So if there is any lone pair in a molecule, we will always give a priority for the arrangements of lone pairs in a position which will give the minimum repulsion, or we will arrange the lone pair in order to get a minimum repulsion. So in the case of trigonal bipyramidal, we will arrange the lone pairs in equatorial plane in order to get a minimum repulsion, which means 120 degree plane, 120 degree angle. But in the case of octahedral, there is all bonds are similar, so we will arrange, anywhere we can arrange. But when there is two lone pairs, we will arrange these lone pairs in 180 degree angle in the octahedral geometry, and we will get a square planar molecule. So we discussed about the lone pairs arrangements in these geometries. The same case is with multiple bonds. As we know, when you are considering the single bonds and the multiple bond is causing high repulsion. So when you are considering this XCO2F2, how you will arrange these XCO2F2 molecule? Yeah, okay. Let's XCO2F2, and then we can also discuss IO2F3. Okay, let's discuss IO2F3 first. So in the case of IO2F3, as we know, there is 2 double bonds with 2 oxygen and 3 single bonds with 3 fluorine. So they will, according to the VSEPR, every molecule in space, every molecule in nature will try to minimize the repulsion between these electron pairs and will try to attain a stable arrangement of molecules in space, arrangements of atoms in space. So, as we know, the repulsion due to multiple bonds is greater than the repulsion due to sigma bonds or single bonds, just because the electron cloud density is small. Because more electrons are shared when we are forming a double bond. So the electron cloud will be more present in the case of multiple bonds than in the case of single bonds. So the repulsion due to multiple bond is very greater than in the case of sigma bonds. So how we will arrange these IO2F2 molecules in the tetrahedral geometry, where you will arrange these oxygen atom and where you will arrange these fluorine atom. Tell me. Keep in mind, we have to minimize repulsion, and the multiple bond repulsion is greater than the single bond repulsion. So how you will arrange it? Just tell me.
The O atoms would be in the equatorial bonds.
Yes. O atoms, which is forming a multiple bond, which is giving more repulsion, we will arrange this in equatorial plane. So it will be O, O, F, F, F. This is how we should draw the IO2F3 structure. This is the actual arrangement, because when you are arranging these oxygen in axial angle, axial bonds, it will cause more repulsion. And when you are comparing this structure is having more stability or lesser energy. So we will always prefer the more stable structure. So this is the structure of IO2F3. And when you are considering XeO2F2, not XeO2F4, which has an octahedral geometry. As we know, all the bonds are similar, so we can draw anywhere in oxygen. But when there is two oxygen or two multiple bonds, we will always try to arrange these two multiple bonds with maximum repulsion, means not with maximum repulsion, with maximum distance or with maximum bond angle. Just because, as we know, the multiple bond repulsion, it's very higher than multiple bond, single bond repulsion. So we will arrange these two multiple bonds with maximum distance or with maximum bond angle. So these two, how we will arrange these XeO2F4, the octahedral geometry, or how we will arrange these two oxygens in the octahedral geometry. Is it like XeOOF?
No, ma'am. I think the oxygen will be in the axial bonds.
Yeah, that is actually, it is not needed. Like the oxygen should not be, we can't say like oxygen should be in axial bonds, because in octahedral shape,
Oh, it's symmetric.
octahedral geometry, all these four bonds are same. And if you are drawing like this,
on the opposite sides, then that'll be
yeah,
the
if
most
you are
repulsion.
drawing like this, also it's fine. Okay, there is not axial or equatorial bond concept, but when we are drawing this XeO2F2, normally we follow a conventional method, like we will first fill these lone pairs in upper and lower. Like that also, we can also draw this. But if you are drawing this also, this is not a wrong structure. That is also fine, because all the four bonds are equal. And this is like, if you are looking like this oxygen is here. But if you are looking in some other way, you will also find it the same. This both are same. Like that, you will, I think you will feel like that. Means if you are looking like this way, this is in the plane. But if you are looking in some other way, I don't know how I will say that. In some other way, you will find this as a square planar structure, and this as upper and this as lower. So if you are drawing like this and if you draw this also, both are fine. And the thing is, the oxygen bond should be in 180-degree angle. But we will prefer this, because the conventional way we used to draw this like this only. So we will prefer this, but if you draw like this also, this is not wrong. This is right. So XeO2F4, it's octahedral. Yeah, and so keep in mind, double bonds will always try to arrange in minimum repulsion when we have sigma bonds and double bonds. And when you have sigma, pi, and sigma and single, double, and also lone pairs, you should first concentrate on lone pair. You should first concentrate on lone pair. You should first concentrate on the arrangements of lone pairs in the minimum repulsion one or in the maximum distance one. Then you should concentrate on double. Then only we will arrange the sigma bond or the single bond. Okay, so that's only. So this is in the case of lone pairs, and the other case is in the case of multiple bonds. And also, the electron cloud density around the central atom, it is also influenced by the surrounding atoms. We already discussed in the case of NF3 and NCl3. We are going to discuss again the surrounding atoms. As we know, we are only concerned about electron cloud density on the central atom when you are talking about BSCPR. So the electron cloud density on the central atom can also be influenced by the surrounding atoms or this electronegativity of the surrounding atom. Okay, so when you are considering an NF bond, okay, let's consider NF3 and NCl3. Both is having pyramidal shape and tetrahedral geometry. And the bond angle of Cl and Cl bond angle will be greater than F and F bond angle. Let's discuss how we will say this. As we know, the nitrogen and fluorine has electronegativity difference, and that is forming a polar bond. Or the shared pair of electron, it is not equally shared between nitrogen and fluorine. Fluorine is more electronegative, or fluorine is a more electronegative atom. It will always try to attract the electron pair towards fluorine, and the shared electron pair will displace it more towards fluorine due to its high electronegativity. When you are comparing it with NCl bond, first you say that fluorine electronegativity. Fluorine is more electronegative than fluorine. So when you are considering the electron cloud between nitrogen and fluorine and between nitrogen and fluorine, the shared electron pair, it is more displaced towards fluorine in the case of NF3 when you are comparing with NCl3 molecule. Just because fluorine means when you are considering NCl and NF bond, just consider NCl, NF bonds separately. So fluorine is more electronegative than fluorine. So fluorine has the ability to attract electrons more when you compare with chlorine. Fluorine has the ability to attract electrons towards themselves as compared to chlorine. Fluorine has the high ability. So when you're comparing the nitrogen and NCl and NF bonds, the electron cloud density around nitrogen will be less in NF. Is it clear?
Yes, ma'am.
We are talking about only about the electron density or electron cloud density around the central atom, and that can be influenced by the surrounding atom. So when you're comparing NCl and NF bond, fluorine is more electronegative. So fluorine has the ability to attract electrons more towards themselves as compared to chlorine. So the electron cloud, when you're considering NCl and NF bond, the electron cloud will be more towards fluorine here when compared to chlorine. So the electron cloud density around the central atom is less in the case of NF bond when compared to when we are comparing it with NCl bond. Since it is less, there will be electron cloud around the central atom, it is less in NF3 as compared to NCl3. So here the repulsion will be minimum, and here the repulsion will be greater. So since the electron cloud density is greater as compared to NF3, the repulsion will be greater in between NCl bond. So the repulsion between NCl bonds is greater The repulsion between NCl bonds is greater when you are comparing repulsion between NF bonds. Since the repulsion is greater, they will try to arrange in maximum distance. So they will increase their bond order. So the Cl-N-Cl bond angle is greater than F-N-F bond angle. This as the, we will finish it in 15 minutes. Sorry, tell us. Okay. So repulsion between NCl bonds is greater, so they will increase their bond angle. Or in general, there is a short means, or you can relate with bond angle. This is a shortcut, and this is the correct explanation. Bond angle is inversely proportional to electronegativity of the surrounding atom. Don't write these things in your exams, and this is a shortcut. Okay, remember this is a shortcut. Bond angle is inversely proportional to electronegativity of the surrounding atom. So when you're considering NF3 and NCl3, fluorine is highly electronegative, so its bond angle will be less. Means high electronegative atom will cause less electron cloud around the central atom, so the repulsion will be minimum, so the bond angle will be minimum. When you're comparing this NF3 bond angle, the bond angle in NF3, it's less than bond angle in NCl3. So just tell me what will be the, how we will compare the bond angle in Ni3, NCl3, NBr3 and NF3. Ni3, NCl3, NBr3 and NF3. So what is the order of bond angle in these molecules?
NF3 is less than NCl3 is less than NBr3 less than Ni3.
Ni3, yes. So is it clear for everyone?
Yes, ma'am.
Okay. So the bond order is NF3, it's less than, NCl3 is less than, NBr3 is less than Ni3. The bond angle order. So this is the order. NF3 is more electronegative, so the electron cloud density around the central atom will be minimum. So the repulsion will be minimum, so it can, the bond angle will be also minimum. Okay, then consider BF3, BCl3 and BBr3. What is the bond angle order?
BF3 less than BCl3 less than BBr3.
No, that's wrong. Just because, okay, so I will introduce two terms. Like this term, it's not a, you don't need to remember. Like I will introduce two terms like ideal case and non-ideal case. This is the case where nitrogen is having one lone pair, right? In ideal cases, where when we discussed about trigonal planar, tetrahedral, pentagonal bipyramidal, or trigonal bipyramidal, octahedral, and all these things, I told you like the repulsion is same, and they will arrange in space in order to minimize repulsion in this case. And when you're considering the case like, okay, the trigonal planar, it's AB3. There is no lone pair and they are arranged in 120 degree in space. And in those cases, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral and pentagonal bipyramidal. In those cases where there is no lone pair, the repulsion means where there is no lone pair, there is only bond pair is present. Only bond pair is present in those molecules, and in that case we will call them as ideal case, or the repulsion is same in every case. Every bonds is having the same repulsion. When you are considering NCl3 or NBr3, there is an influence of lone pair. Right. There is an influence of a lone pair or different types of repulsion, different repulsions, different magnitude repulsion is occurring here. Right. In these cases only we concern about these electron negativity, or we will only concern about, in these cases only we will concern about the surrounding atoms. Or I can tell you, the ideal case is where the case in which the repulsion is same. Repulsion due to each bond or repulsion is same. In ideal cases, the repulsion is same, and in non-ideal cases, the repulsion is different. Or okay, the ideal case the repulsion is same, and normally the ideal case is the case in which molecules form with no lone pair. And the surrounding atoms will be same. Surrounding atoms will be same.
So, ma'am, it'll all be 120 degrees.
Yes. All the
Alright.
atoms will be 120-degree. Like if I will explain that. So ideal case and non-ideal case is there. Ideal case means all bonds is having the same repulsion, and those ideal cases are the cases which like linear, trigonal planar, pentagonal bipyramidal, trigonal bipyramidal, and octahedral. And all the atoms should be same. Like if you are considering XeO2F2, which is also octahedral XeO2F4. It is also octahedral, but the atoms are not same. Or XeO3F, okay, XeO3F3, it is also octahedral, but there will be bond angle difference because due to the presence of double bonds, there will be repulsion difference between these bonds. Are you getting my point? But when you are considering SF6, all bonds are equal, or all bonds are same. So they will have the same repulsion between these two bonds. And there is no lone pair. So in the ideal case, the molecules with lone pair, no lone pair, and surrounding with the same atoms, that is called an ideal case. And all those case, it is okay. That BBR3, BCL3 explanation I will give. This is called ideal case. And in non-ideal case, like repulsion will be different. And in that case, lone pair will be, either lone pair will be present, or it will surround with different atoms. So the presence of either lone pair will be present, or it will surround with different atoms. So in the case of BCl3, BBr3, and BF3, what is happening? So this is BF, 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 BCl, 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 and B, BR, BBR, and BBR. Okay, we can also say like fluorine is more electronegative and fluorine will attract these electrons towards themselves. These all are happening and the electron cloud around the boron it's also less, means electron cloud around the central atom is less here. But all these having the same electron cloud around the central atom or electron cloud around this bond. Let's take it as okay, just assume this is an ideal case or this is an imaginary case. Just assume I'm giving a value to the electron density around the central atom. Since fluorine is highly electronegative, they will attract these electron clouds towards fluorine. And let's take it as it is having an electron cloud density which is having one value, right? One value. Let's take it, I'm giving a value. So this will also have one value and this will also have one value. And the chlorine, which is not as much electronegative when compared to fluorine. So it is not having an ability to attract electrons. Their ability is less as compared to fluorine. So it is having a 2 electron cloud. It is an ideal case. So it is an imaginary case. And bromine, it's when you compare to the electronegativity. Yeah. When compared to the electronegativity, bromine electronegativity is very less as compared to fluorine. So their electron attraction power is also less when compared to fluorine. So the electron cloud density may be like 3 is present. But all are same. When you're considering the electron cloud density on bromine is same, means both 3 are same. So they will arrange in 120 degree. And these, when you're considering BCl, both are same. Both 3 are same. So they will arrange in 120 degree. And this also they will arrange in 120 degree. I'm not sure, is it clear or not? Let's consider the linear, means those cases with no lone pair. Those cases with no lone pair, you don't worry about anything. You don't worry about the surrounding atoms or anything. Okay, if it is like, okay, this case, it will be 120. If I'm talking about BF2Cl, if I'm talking about BF2Cl, the bond angle will be different. Like when you're considering BF2Cl, the electron cloud due to BCl bond is greater, right? Is it clear what I'm telling? Is it clear for you?
Yes, ma'am.
So if you are considering BF2, if it is, means anybody, those who are not understanding this, just tell me, okay? So if you are telling BF2Cl, the chlorine, as we know, the chlorine is not as much electronegative than chlorine, or fluorine is more electronegative. So fluorine will attract electron cloud more towards themselves as compared to chlorine. And the electron cloud around the central atom due to the BCl bond is more when compared to two BF bonds. Okay, so how it will be? The bond angle, in this case, all bond angle will not be equal to 120 degree. Since the electron cloud around the central atom, it's more in BCl, they will try to increase the bond angle here. They will try to increase this bond angle. Or
Are we assuming that there is a lone pair or there is no lone pair?
No lone pair, but their repulsion is different.
Yes, ma'am, I got that.
The ideal case will be no lone pair or surrounding atom would be same. Since here there is no lone pair, but the surrounding atom is different. So surrounding atom is different. So the electron cloud means according to the electronegativity, fluorine is more electronegative and it will attract more electrons towards themselves, towards fluorine as compared to chlorine. Right? Is it clear? Fluorine is more electronegative than chlorine, so it has the ability to attract electron cloud more towards fluorine as compared to chlorine. Is it clear? Fluorine has
Yes, ma'am.
high electronegativity, so it will have the ability to attract electrons themselves, or the shared pair of electron will displace it more towards fluorine when you are comparing with BCl bond. So the electron cloud density, let's consider like electron cloud density around the boron atom, it's less as compared to electron cloud density due to this BCl bond. Let's consider it is giving 1, it is giving 1, this will be 2. The electron cloud density around the central atom is more due to the BCl bond when you're comparing 2BF bond. So this repulsion will be more. And this bond angle, there will be a slight difference. This bond angle will be less than 120 degree. This will be greater than 120 degree. And this will be greater than 120 degree. In order to minimize repulsion. Think. I can only say that. Just close your eyes and just keep on thinking about it. Then it will be clear. Fluorine is more electronegative, so the central atom electron cloud due to BF bond, it's less due to BCl bond. So when you're comparing electron cloud density in on boron due to BF bond and BCl bond, the electron cloud density due to BCl bond is more. So there is means this type of questions will not be there in for your board exams and all those things. But if you are preparing for JE, you should know this concept. You should know this, you should have this clarity. Where this ideal case and where this non-ideal case. If there is a lone pair, we should concern about the surrounding atoms. Or if the surrounding atoms is different, there will be a difference in repulsion. So there will be some slight change in bond angle will be there. So in the case of BF3, BCl3 and BBr3, the bond angle is same. BF3 bond angle is equal to BCl3 bond angle is equal to BBr3. Both are equal to 120 degree. Okay, I will give you an homework. Draw the structure of PCl3F2 and PCl2F3. Draw the structures of PCl3F2 and PCl2F3. This is your homework. Try to do that. Keep these things in your mind and draw these structures. Then we will discuss these structures in the next class. Okay, and also read those dipole moment concepts. We'll start dipole moment and we will finish it in the next class, and we will start molecular orbital theory in the next class. So be prepared. So read those concepts, dipole moment and Fajan's rule. I thought Fajan's rule is not there in your syllabus, but it's there. So we will discuss Fajan's rule and dipole moment in the next class. Okay, and draw these structures. Try this. This is a concept-wise question. Try this. PCl2F2 and PCl3F2 and PCl2F3. This is actually JE level question. So try this. Okay. This is your homework. Yeah. So we will. Okay. Don't leave. I think Lilith is there. She need to tell you something. I'll call. Okay. Sorry, he.